All right, welcome everyone. Thanks for joining the session on columnar shuffle design. We have Binwei Yang for a senior engineer from Intel here. So we'll do about half an hour of content, and then we'll save the remaining 5-10 minutes for Q&A at the end. Thanks.
Thank you, Simon. Hello, everyone. Good afternoon. My name is Binwei Yang. I'm from Intel, and today I will introduce the columnar shuffle design in the Gluten project. So I will give more details later. So about us, so we are from the Intel Big Data Analytics team. So we started the Gluten project in 2020 May, and we boosted by TPC by 1.8 performance times and TPC-DS by 1.5. And later, we transformed to the Gluten project in January 2022. And so the problem is that we noted that the Gluten project, its performance is limited by the arrow library. And then in 2022, Facebook reached us and asked us to take a look over the Velox library, and we started to evaluate the Velox library and noted that the Velox library has much better performance than the Gluten we used, than Apache Arrow library we used. So we switched to the Gluten project in 2022. And the difference from the Gluten and the Gluten is that the Gluten uses Apache Arrow-based library. It's an in-house designed library, and most of the functions are implemented by ourselves. So the Arrow library itself has a very limited functional coverage of the circle engine. And the Gluten project, the Gluten itself is very similar to offload the Spark SQL to the third-party libraries, including the Velox and the ClearHouse. So Intel worked with Facebook on the Velox library only. And we also use the substrate plan to pass the Spark plan, physical plan to the Velox library, and then start the Velox pipeline. So we have a Spark session in last year. So I listed the website here, and also we have the Gluten project is totally open source on the GitHub. So the link is here. Why we care about the Spark Shuffle? So this chart is the latest performance data over the TPC-8 breakdown. So it's broken by the operators. You can see that the first operator is over the TPC, it's the table scan. So in this test, there's no IO bottleneck. We use a very powerful SSDs, and it's tested on single node. So there's no IO bottleneck. The CPU utilization can reach 100%. So in this case, you can see that the first operator is the scan. The second operator it's a hash aggregate, hash join. It's the third one, and then it's the compress. The compress operator, it's how we compress the shuffle data. So it takes 9% of the total time. Then it's not counted, means it's not counted in our metrics. Then it's a split. The split function, it's input a record bunch, and then we need to split into four different reducers. That's how the split. And it takes 7%. And then it's the ShuffleWritter, we need to write the data to disk, it takes 6%. And then there is another one, it's the stream input. It's how the reducer read the data and start the pipeline over the reducer side. It takes 6%. So totally, the shuffle-related operators takes up to 22% of the total elapsed time. So it's a very hot operators in the list. That's why we need to take a look over the shuffle. And first, I will introduce the Spark Shuffle. The Spark Shuffle, you guys may be very familiar with that. So it's a repartition of the data according to the partition key. So the partition key, usually it's the hash key or hash join key. So it put the same partition key, the same set of the partition key into the same partition for each reducer, and then the one reducer pick up the data and start the reducer pipeline. So how the reducer and the mapper exchange the data, that's how the shuffle happens. And related to shuffle operations, there are several operations here. The first one is the split. It's a split. So the split is how we split the source record bunch to the destination record bunch, and then it's the serializer. We need, after the split, we get the destination record bunch, then we need to serialize it as flat memory, and then we do the compress. If memory is not enough, then we need to spill the data to disk. And after the shuffle, after all the record bands are processed, then we have the persistent. So we need to save the data to local disk. That's how the Spark have the fault tolerance feature. And then the shuffle side is done. And when the reducer side read the data, then the mapper side need to load the data from disk, then send the data from the through NAT network. And then the reducer fetch the data and do the decompress, and then do the deserialize, and then get the internal row format or the columnar format and start the reducer pipeline. So this is how the shuffle, how the operators how operations happens in the shuffle. And currently in Spark, there are two types of shuffle. First one is a bypass merge sort shuffle. So it's a hash-based shuffle. We need to hash the data and then save the small partition for each reducer into a single file. And then when all the data are splitted, all the data are processed, we need to merge all the files, copy these files into a large file, and then send it to driver, and the driver start to send the file to the reducer side. And another one is the unsafe sort right? So this is another commonly used. What I do is that when we get the source of the data, we sort the data from the beginning to end, sort the whole partition data, and then it's an external sort. So if we need to, if the memory is not enough, we need to spew to memory, spew to disk. And after we sort the data, then we can easily divide the data set by the partition ID. Because we already sorted the partition ID, then we can pick up this partition ID for this reducer and that partition ID for that reducer. So we can, after the sort, we can get that. So these are two most commonly used Spark shuffle in commonly ShuffleWritter in vanilla Spark. And then let's introduce about the columnar shuffle. So when we design the Gluten project, it's a native implementation of the Spark SQL engine. Its basic data format it's the columnar format. It's not the row format. So the columnar format is really friendly to the data analytical processing. And once we implement the columnar format, we cannot reuse the Spark row-based shuffle. We have to use design a new columnar shuffle. So the columnar shuffle is we need to rewrite everything, almost everything in the shuffle, including the split, the serializer, compress, spew, and the precision, everything. But we reuse the Spark load-based, the Spark shuffle service. So how the data is transferred from master side to reducer side, we still reuse that control logic. It's not changed. And then on the reducer side, how to decompress the data and how to deserialize the data is also redesigned here. And when we design the columnar shuffle, firstly, we know that for the columnar data format, for the columnar operators, for the columnar data format, the hash join, hash aggregate, they are friendly to columnar process. But one operator is really not friendly to columnar process. It's the sort operator. It's because that when you not only need to sort the key, after you sort the key, then you need to serialize or need to materialize the payload. You need to pick up every row, every column, pick up the data from every column. Then the pickup process, it's a random access over the memory. So you need to, it's not a sequential. To the CPU, the random CPU memory access is very, very expensive, much more expensive than the sequential access. So it's not only because the cache line is 64 bytes, or it's also because that the hardware prefetch or software prefetch can hardly work better. So the sort operator is not friendly. That's why we need to use the hash-based shuffle here. And the hash-based shuffle, it's similar as the vanilla Spark hash-based shuffle. Firstly, we have the record bench. We have the record bench here, and the input, it's a serial of a record bench in a partition. Then we do the hash over the partition key, over the shuffle key. And then according to the hash results, we put the data into different reducer for different reducer. And then the memory, when we do the split, the memory is pre-allocated. I will talk more detail later. And once all the data is shuffled, then we write all the partitions. We write all the data to a large file, and it's placed in the memory, and placed the file, and then send it to reducer. It's similar. It's actually very similar as Spark, vanilla Spark shuffle-based shuffle. The difference is only that we hash the data, we hash the key, and then get a column format. We need to process the column by column. And this is how the spill happens. So when we design the hash-based shuffle, we must handle the spill because the memory is definitely not enough. So once we have the native implementation, the memory consumption is much less than vanilla Spark. It's only 1/6 or 1/8 of the vanilla Sparks. So the spill for the same block, for the same size of the partition, the native implementation don't need a spill, but the vanilla Spark needs a spill. But we can decrease for the Gluten, for the native process, we can decrease the spill a lot. It's actually one performance boost from the vanilla Spark. But we cannot avoid the spill because your partition is maybe too large. So when the spill happens, what the spill happens here is that after the split, we get the partition reducer, get a reducer partition from, get a reducer record banks in the memory, and then we need to compress the memory, compress the record banks, and then save the memory, save the record banks into another memory, another block of the memory, and when we save to another block of memory, it's a cached bench memory. When the cached bench memory grows, it keep growing. And once the memory is out of memory, it's run out, then the memory allocation will trigger the Spark memory management, and the Spark memory management will call a spill interface. And the spill interface will call into the shuffle operator, and the shuffle operator will start to spill all the data cached in the cache memory, and then it's saved into a single file, and then it's free the memory, and then it starts the next split operator. And once all the record banks, all the partitions are processed, then we need to do the merge from in-memory, the cached branch, or from the files. So this is how the spill works. So for each out of memory, we spill all the data into a single file. It's sorted by the partition ID. And in this way, we can solve the small file issues over the hash-based shuffle. So this is how the spill works. And then this is how the merge works. So when we save the data when out of memory, we save it by the partition ID. It's sorted by partition ID, and we catch the position of the offset and the length. And each out of memory will have a single file, and then when we do the merge, we read the file, we read all the files, and then we put all the record banks over the same partition ID together, and then save it into the large file. So it's when we do the merge, the single file or the small file, it's also sequential read, and the large file, it's a sequential write. So there's no random read here, random file access here. So similarly, the random file access is much more expensive than the sequential access. So this is how the merge works. And then after we implement it, we need to support the remote shuffle service. The remote shuffle service is very widely used in the customer side. So what we do is that once we have the record bench split, after the split, have the record bench for each reducer, we just send the record bench to the remote shuffle service. It's serialized and compressed to the remote shuffle service. And the remote shuffle service take each record bench as internal rule. Actually, it's just a block of memory. It doesn't care it's the internal rule or it's a record bench, serialized record bench. It's just the one rule over the data. And then the reducer side, when the reducer reads the data, it requests the data from remote shuffle service according to the partition ID, and then the remote shuffle service will get the data. So all the data processing is related, it's a record bench. And also the push-based shuffle, it's a new feature of the Spark 3.4, 3.3. So the push shuffle is that when we have the record bench, split, then we compress it, serialize it, and then send it to the reducer directly, and the reducer caches the data of each mapper. and then it can start the pipeline once all the member side finishes their work. So once the reducer stage start. So this is a push-based software. It's also it's very similar to remote software service. So the difference is just that we send the data to remote software service or to the reducer. And then let's talk about the split function. The split function is actually very, very sensitive, performance critical. The split function, so there are several implementations. We can split the record bands by row or by reducer or by the column. So we have many tests, and then we eventually what we used is it's the 3 loops. The first one is for each column. The second one is for each reducer. So we fill the reducer over each column, and then there is another the third loop. It's the row. And we have a new array, it's called the offset, column offset, and then it takes input over the row number, row index, and get the output, get the offset over the row, and then we save the data. It's a 3 loop here. And what happens is not like this. So we save, firstly we fill the record bands, the reducer 0, then we fill the reducer 1, and then we fill the reducer 2 here. And you can see that here, the memory access over the column 1, it's a random access. You can see, so it's not a sequential access. It's a really random access. And after we finish the column 1, fill the column 1 over its reducer, then we start to fill the column 2 and all. And also you can see that when we do the split, the reducer, the destination memory must be pre-allocated. It's performance critical. It's because that when we fill the data, if we didn't pre-allocate the memory, then there will be a resize over this memory, and the resize over the memory may lead to a mem copy. The mem copy is expensive in this process. And also you can see that each column is scanned over a reduced number over the times. So each column is scanned many, many times. And the key is that we need to keep the column data into L1, L2 cache. It's performance critical. Once the data is saved in memory and you will have a random memory over the reduced number of times, then the performance will crash definitely. And it's because that it's the column access, it's a random read access, and the column, the destination write, the reducer field, it's a sequential write pattern. And this is how the memory works. So first, we are introducing 2 blocks of memory. The first one is the source memory, and the second one is the target memory. The source memory is controlled by number of rows multiplied by the data size of each column. So for int, it's 4 bytes. For int 64, it's 8 bytes. So once we need to make sure that the number of rows multiplied by the data size is fit into the L1, L2 cache. And if the number of rows is 4K and its int column is 16K. So 16K can be fit into the L1 cache. But during the process, not only the data, not only the source data is saved in the cache. So there are several other processes, several other data structure. It must be saved in the L1 cache as well. And on the reducer side, the problem is that so we need to pre-allocate the memory. But if we pre-allocate the memory, what the size is that the data size, the column data size multiplied by the row number, multiplied by the number of columns, and then multiplied by the number of reducer, and then it's multiplied by the executor cost of the system, and then it's the number of executors. So, for example, if we have a 4K row, 8 columns, int columns, and a 1K reducer, 256 threads, then it's lead to 32 gigabytes of the total memory. So it's increased very, very fast. It's multiplied over all these factors. It's increased very fast. So once the memory is not enough for the reducer, so this memory it's preloaded. So if this memory is not enough, then we cannot do the process at all. So to serve this memory, we have the first one is that the memory allocation. It's for each reducer, it's delayed. So we didn't pre-allocate for every reducer. Once the reducer is touched, then we save it. And the second one is that the target rule is calculated based on the available memory and when the first record bunch arrives. And it's by default is 4K or 8K, and we can decrease that. And but the problem is that the less rule number, the higher overhead of the bunch switch. So it's because that we process the data bunch by bunch. Once the rule number decreases, which means the bunch number will increase, and each bunch switch has a very big overhead in the pipeline, and then which lead to poor performance. And also, we are talking about the experimental salt-based shuffle. So, and then we need to take a look if that's the plan B. So if the problem, if we cannot do the hash-based shuffle, the memory is really not enough, or the columns or the number of reducers is really very large, we cannot do that, then we can fall back to the salt-based shuffle. But till now, what we see from the customer side is that the hash-based shuffle works very well. It's because 32K, 32G, it's still okay. Oh, sorry. And this is the split performance. So you can see that it can scale from the columnar number. It can also can scale from the reducer number, from algorithm, we can see that. So the column number increase is okay, reducer number is okay, but the column data size is not okay. So here, the first point is 4K, and the second point is 8K, and then it's 16K, 32K, just increase until 4 megabyte. And the output count size is 2 megabyte in this test. And you can see that if the record bunch size is very small, then there is much overhead. The elapsed time is high, but when the record bunch size increases, then the elapsed time will decrease once the data fits into the L1, L2 cache actually. But once it exceeds the L2 cache size, then it's a random size over the column, then the performance will drop seriously. And in this test, it's actually a round-robin split. So it means that we split the data by its reducer. Reducer 1 get number 1, reducer 2 get number 2. And the hardware prefix actually works well. It's because there is a pattern there. There is a pattern. It's a round-robin. You get the number 1, number 7, number 14, just like that. And even in this way, the performance is still dropped a lot. And if it's really a random access, then the performance will decrease by 100, maybe 100 over times. This is the split functions. And also after the split function, let's take a look over the compression. And how the compression is important is that it's not only the compression time, but also the compressed size. So here we can see that on the single node, we can get 2.4 times performance better. It's no I/O bottleneck, no shuffle. There is a shuffle, but no network access. And this 2.4, it's the older data. Oh, I forgot to mention that currently our TPC it's three times better already. And here the data is older data. It's last quarter data. And on single node, you can see the performance boost is 2.41. It's very impressive. And then if we run on 3-node cluster using 100 Gbps network, then the performance boost decreased to 2.13. So it's because the network it becomes a bottleneck. And if we use the 25 Gbps network, which is commonly used from the customer side now, and once we use 25 Gbps network, then the performance dropped. The performance boost dropped. Actually, the performance is still much better by Vanilla Spark, but the performance boost ratio dropped to 1.79 times. And here, this chart shows how where the bottleneck is. So firstly, you can see that the Vanilla Spark, the shuffle data size. The shuffle data size is actually different. The columnar data format has less shuffled data. It's because that the columnar format is more friendly to the compression algorithm, because for example, you have the line item key, then the key starts from 0, 1, 2, 3, just like that. It's very friendly to the compress. So that's why you to shuffle the same data, to shuffle the same, and the shuffle data size actually it's the Gluten, the native implementation has less shuffle data. But if we look at the network throughput here, the vanilla Spark is 4 gigabytes per second, and the Gluten increased to 7 gigabytes. It's because that the native implementation has it processes the data faster than it needed to put more pressure to the network. Its network throughput will increase more pressure. And also, if the network is a bottleneck, then its CPU utilization will drop from 81 to 71, 10% of drops. And the solution is very simple. First, we change the network, use a faster network, or use less data here. And then we have the accelerator. We have a QAT accelerator integrated into the fourth generation of the Intel Xeon processor. It's a QAT processor. So the QAT accelerator is introduced several years ago, but it's a PCIe board. It's not integrated. But on the fourth generation of the Sapphire Rapids, we integrated. And if we compare the RE4, the default algorithm is RE4 under QAT, and also with the ZSTD, you can see that the x-axis is the compression ratio, and the y-axis is the compression time. You can see that the QAT has the same compression time as RE4, but its compression ratio is almost the same as the ZSTD. And this is how the performance boosts from the QAT. If we use the QAT, then we can have a higher compression ratio and lower and the same compression time as RE4 and less compression time as the ZSTD. So you can see that if we compare to RE4, the performance boosts by 20%. So you may ask that how much performance boost from ZSTD. So ZSTD is 7 to 9%. It's according to how the compressed algorithms is. And also, we are still working on the process to optimize the QAT. And then let's talk about the reducer side. So the reducer side doesn't change much. So currently, we almost reuse all the Sparks. So the reducer has different memory block, fetch the memory block in async mode, and then save it in a buffer. Then the next pipeline, the reducer pipeline will start after the data is fetched and decompressed. But the difference is that currently, it's because the data is organized in record bands. So the compressed data and the saved data, it's all organized as record bands. And so when the reducer reads the data, it doesn't need to read the whole block of the memory. So currently, the vanilla Spark implementation is that it must read the whole block from one member. And once all the data is fetched, then it starts to decompress it, and then it starts to start the reducer pipeline. But since the columnar format, it's columnar, the record bands are organized, then we can start the reducer pipeline once one record band is fetched from a remote side to the buffer, and then we start it. So that's the only optimization. So the unit decreased, and then we can have less, we have more overlap, and we can have less start times. And one block it's the size of a reducer. So that's all over the thing I want to highlight today. And under example, the first one is that with native SQL engine, with the native SQL engine implementation, the columnar shuffle is a key operator, and you see it's almost 1/3 of the total performance. And the second one is that the column shuffle, it's their unique challenge. It's different from the rule-based shuffle. We need to did lots of experiments and find the best solutions. And even till now, I believe that it's still not optimal. We still need to optimize it. And also, accelerators can be effectively used in the shuffle here. Okay, that's all. Any questions?
Thank you, Binwei.
So I think Simon just told me that it's a very technical one. So I'm not sure how much you can follow. So if any questions, if you are interested in the Gluten project, you can ping me offline.
All right. Thank you, everyone, for joining. Please remember to rate and review this session as well. Thanks.